continuing on from there, right, this is a very typical, something you'll see in big chem is that all these different graphs are and very complicated, right? This is a three-dimensional graph of the pressure versus the volume versus the temperature of an ideal gas, right? And instead of having a line like we would in a normal two-dimensional graph, now we have a surface or a plane through a three-dimensional graph. Right, so depending on where we're going on this particular graph, we have different things. Right, we see in this line here where we have constant temperature. Again, it's hard to see a little bit because it's three-dimensional, but this would be constant temperature. Right, that's the isotherm. We have the same temperature. Right, we see as we alter the pressure or the volume at the same temperature, we see how the other one changes. When at constant pressure, isobar, and at constant volume, right, it's hard to see. Constant volume would be an isochore. Isochore is not one we're not gonna use that word all that much, to be honest. So not really important. All right. Now, when it comes to our ideal gases, we mix them together. All right. There's only going to be one rule for an ideal gas. Right. Treat every gas as if we're the only one present. Right. Real gases, this is not going to be true because our ideal gases, we're assuming that there is zero interaction between all the different gases. That's what makes them ideal or perfect gases. And real gases, not true. Right. These mixtures of gases will be in the same container, so they're going to have the same volumes and the same temperatures. And otherwise, they would not be mixed. Right. Each gas will exert a different pressure, though, based on the amount of that particular gas. Right. Again, if we're looking at PV equals nRT, right? R is a constant. If T is constant, the same, and V is the same for each one of them, then the pressure is going to relate directly to the amount of moles, right? And the different pressures exerted by each gas are going to be called their partial pressures, right? The partial pressures, because they're going to add up into a total amount of pressure, right? As I say right here, if you stack books on a scale, you will read the total weight of all the books, right? You can think about each book having a partial weight, right? Adding up to a total weight. Same exact thing with the partial pressures and the total pressure, right? When we measure the pressure inside of the container, we can only measure the total pressure, right? Just like a scale can only measure the total weight of the books, right? Our total pressure is simply, though, going to be the sum of each individual pressures, individual partial pressures. In this case, helium and nitrogen and oxygen. We put 1 atmosphere of pressure, each one of these in the same container, same volume, same temperature. We would expect a pressure of 3 atmospheres. Pretty straightforward, because then pressures are, again, sort of like weight, but also sort of not. All right. Last thing to mention here is mole fraction, right? Mole fraction is a useful way to talk about gas mixtures, right? Because it's going to depend on the number of moles of everything, right? Depends on the moles of each gas, right? So knowing the mole fraction can help you decide what fraction of the pressure, the total pressure, is applicable to that one gas. All right, so our mole fraction here is chi, Greek letter chi. Come here, and there we go. Trying to get it right. Greek letter chi, there we go. All right, so the mole fraction of gas A is going to be chi sub A, which is the total moles of, the moles of A over the total moles of everything. All right, another way of saying it is going to be, right, the part over the total. That's all we're looking at, part over total. That's what our mole fraction is, right? And if we multiplied it by 100%, we would change it into percentage instead of a mole fraction, right? But a mole fraction is always going to be between 0 and 1 because that's an actual number, right? Now, since our pressure and our moles are related in a gas mixture, the partial pressure of a gas is its fraction of the total pressure. the partial pressure of gas A is the mole fraction of gas A times the total pressure of the gases, assuming everything's going to have the same temperature and same volume, which is a very safe assumption because they're going to be mixed in the same container. Oh, there we go. Go backwards. Here we go. So an example here, 4 moles of nitrogen dioxide decompose into nitrogen and oxygen gases, a rigid 10-liter container at 300 Kelvin. And what are the pressures of the product gases? And what is the total pressure? All right, so if we do this, there's several ways of us doing this actually. But the first way we're going to do this, we're going to use the chemical equation. And if we have 4 moles of NO2, that's going to decompose, right? If 2 NO2 decomposes into 1 nitrogen and 2 oxygens, right, then 4 should decompose into 2 nitrogen and 4 oxygens, right? So what we would expect 2 moles of nitrogen and 4 moles of oxygen. So we start here with 2 moles of nitrogen and 4 moles of oxygen. Excuse me. Right? Or we get added up 6 moles of gas total. Right? 6 moles of gas total. So there's 2 different ways of doing this. We'll use the way that uses the mole fraction. Right? So if we start with our ideal gas law, we're looking for a pressure, the total pressure, right? Our volume is 10 liters. Our moles, there are 6 moles of gas, total gas, right? In this case, since we're using liters and moles, well, you know what, let's do this in terms of the R value we just used previously, 8.314 times 10 to the negative second decimeters cubed, which is the same thing as a liter, right? Bar per mole Kelvin, right? And temperature of 300 Kelvin. Right? And if we would do that simple little equation, right, we would do 6 times 8.314 e negative 2 times 300 divided by 6 gets me, or divided by, 10. Let me go backwards. And what that, give me that number, right? Divided by 10 gets me 14.96. 14.96 in this case, bar of pressure, right? Because the R had values of bar. Right? That's the total pressure. Right? It's the total pressure. Right? If P of each part is chi of each part times the total pressure, right? Well, we need to figure out the mole fraction of each one. So the mole fraction of N2 is going to be 2 moles of N2 divided by the total number of moles, which is 6, right? So that's going to be 0.333 repeating, right? 2 over 6 is 1/3, right? The mole fraction of oxygen is going to be 4 over 2 plus 4, which is going to be 0.667, repeating, 2/3, which is repeating, right? So our pressure of nitrogen is going to be 0.333 times 14.96 bar. Okay. And our partial pressure of oxygen is going to be 0.667 times our 14.96 bar. Right. If we do a little bit of rounding, we'll do a little bit of rounding to make things nice and neat. Right. This for nitrogen, we have 1/3 times 15, basically, right? 1/3 of 15 would be a partial pressure of 5 bar. Right? 1/3 of 15 is about 5 bar. That makes it really nice. All right, over here for oxygen, all right, 2/3 of basically 15, right, is going to be 10 bar. A little bit of rounding makes things come out a little bit more nice and even, right? But that's some fairly simple, perfect gas stuff. Really just a review from Gen Chem. All right, nothing super special there.